Good afternoon, everyone. My name is Pik Patana Montong Tanunam from the University of Melbourne. I will be a session chair, a replacement session chair today. And we have a lot of interesting talk today. And the first one is by Changsha. And he will present the paper, Present Them All, a universal learning representation of bug reports.
Thank you very much. And good afternoon, everyone. Today, I will introduce our paper. My name is Zhang and come from Macau University of Science and Technology. The title is Present Them All, a universal learning representation of bug reports. Okay, let's go. We have known the bug reports can help developers and researchers to fix bugs or know how to know the location of these bugs, right? And also we can depend on bug reports to conduct a series of automatic software maintenance tasks, such as duplicate detection, severity, and priority detection. Also, we can conduct some generation tasks, such as bug report summarization, okay? So this figure shows an example of bug reports. We know that there are a lot of features. Generally, yes, MSR researchers also utilize the title and the descriptions to train the model and to find some interesting rules, right? Also, someone like to utilize the comments and to analyze how to fix the bugs or find where the bug is, right? Also, we know that there are some features such as severity level and priority levels. These levels can help the developers, quick understand how the bug is and find the location of these bugs, right? Okay, so but in the previous studies, these models have some problem. The big problem is they consider to use the single model to conduct the single task, right? If you want to use the single model to conduct the multiple tasks, it's very difficult. And due to the complexity, cost, and comparability, right? Because you should change some parameters of this model and remove or add some layers, so it is more difficult, right? So for our paper, we propose a universal model to conduct multiple automatic software maintenance tasks. Yes, this is amazing, right? So we consider propose the one model to conduct multiple tasks. So for in details, we train in the pre-train process. We consider the dynamic model, masked language model, and the contractive learning. We name the find yourself. And by utilizing the two new competence, we fine-tune this model and to conduct multiple tasks, such as generation tasks and the classification tasks, right? So for our method, in the process of text encoding, we utilize the byte level BP, okay? And to this method can resolve the OOP problem, and also resolve the problem of modeling large and the diversity control, okay? For the input and output representation, we consider to utilize another method to represent the bug reports. We consider both of word embedding and position embedding, okay? And for the output representation, we also output the two parts. One is the universal context representation of each token in bug report sequence, and another one is contextual representation of CLS. Okay, so for the model, we consider to start with the 12 bidirectional transformer encoding layers. Actually, we both consider the scarce multi-land attention and the feed-forward network. Okay, so that it can well capture the contextual information of bug reports. Okay. So for the dynamic masked language model, we select the 15% of tokens in bug report to mask out. We also consider the 3 different methods. Okay, the mask token with 80% probability, and the random taken with 10% probability, and the unchanged work with 10% probability. Okay, so for the contractive learning, why do we want to use the contractive learning? The major reason is we should consider the positive instances and the negative instances. So we find the way and to represent this part, okay? Finds these negative instances. That finding the negative instances is important for our method. So we propose a find yourself, and by utilizing the contractive learning. Okay, so when we finish the pre-training the process, we consider to fine-tune this model. And for the classification task, we end the classification layer. For the generation task, we consider to end the auto-regressive decoder and to produce the sequence, okay, sequence to sequence. So for the experiment and for the data size, actually for the for the 3 tasks such as the bug report summarization, bug severity, and priority prediction, we utilize the traditional data sets, including Mozilla, Eclipse, NetBeans, and GCC. Okay, and for the duplicate bug report detection, we consider utilize the this open office data set. So for the research question 1, we employ the how effective is RepresentThemAll when compared to the baseline approaches. Because we conduct a lot of experiments in 4 automatic tasks, okay? And for the bug report summarization task, we consider to compare the deep sum, bug sum, PR head, and transformer. And this table shows our algorithm performs better than others. Okay, so for the duplicate bug report detection, we know that our algorithms also improves than other algorithms, but we know that the improve is limited because these models performs better, right? So the improvement space is limited. So for the priority and severity prediction, our algorithm RTA performs better than others. The improves achieves from 10% to 20%, right? So we have this conclusion by using this universal model. RepresentThemAll can replace existing approaches to handle different tasks in software maintenance. So the research question 2. How effective is RepresentThemAll when compared to other pre-trained language models? We compare to BRT, Robota, and CodeBoard and SC board. Okay, so our model shows better than the other models because we can learn the domain knowledge related to bug reports in the pre-train phases. Okay, so for the research question 3, we explore how does find yourself objective contribute to the performance of our method, right? So we removed this component and compare the whole model. We find that if we remove the find yourself component, the performance decrease. So we demonstrate that these components have some contribute and to the whole model, right? So we conclude our method. We find that this algorithm performs well in the classification tasks and generation tasks. So we, open the source code in the Hugging Face, and you can download this transformer and to conduct these tasks. We also published how to fine-tune this model and also open the all experimental results data in our GitHub repository. So you can also find this way and to conduct these experiments. So that's it. And maybe if you have suggestions or comments, and you can also discuss with me. Oh, thank you very much.
Yes, thank you for the great talk, Steffen Herbert from the University of Passau. So for completeness, we did ZBERT, so I have some interest in this, but what I'm really wondering is, why is this so good? So usually when we pre-train transformer models, we use gigabytes of data. From what I've seen, you haven't. So you have about, I would say, a tenth of the pre-training data of BERT, and the model size, if I've seen it correctly, is the same as BERT base, and the training is also similar to BERT base, but you have this contrastive step. You've already shown us the contrastive step helps. So what's your hypothesis? Why is this so much better? Because, I mean, you showed that it beats all other stuff, but based on the common knowledge we have about large language models, it shouldn't, right? Because you're not throwing too much data at it as everybody else is.
Okay, I think that is a very good question. Okay, we also know actually there is a problem because AI model has lacks of the explanation. So actually, if we want to explore the deep reason to how this model performs better, actually this is a difficult question. But I want to, from the other aspects, to demonstrate this point. For example, we built this new transformer by starting with the 12 bidirectional transformer. We found that this 12 bidirectional model performs better because this model can well learn the contextual information in the bug reports. Because we know that the text, the contents of, for example, the description in bug reports, including natural language and some source code fragments. So that is a problem. So before the pre-training the model, we utilize the BBPE to encoder this. Combining hybrid information, including the context and the source code fragments. So that is the first reason. The second reason is we consider the mask language model. Actually, we max the different area 10 times, and train this model and can well capture the information. I think that is the second reason. I think, yeah.
But I mean, that's what BERT does.
Yeah.
So, I mean, the question was better than BERT. You know, explain the
yes, better than BERT.
BERT does. So why are you better than BERT if you're doing exactly the same things as BERT?
Yeah. Yes. We know that actually BERT and Robota also performs well. So we improve this performance, right? And so we consider the two new components and utilize the different encoding method. And actually, I think the main contribution of this paper is to propose a universal model, right? But for example, if we use BERT, But we only use the boards conduct the single tasks, right? For example, bug report detection. Okay, if we utilize the classification layer in boards, but it can also performs better in a duplicate bug report detection task. But it's difficult to perform well in other tasks, right? So in this model, I think the main advantage is to build the universal way and to conduct multiple tasks at the same time, right?
All right. Thank you so much. And now we need to move on to the next presentation. So please join me thank the presenter one more time.
Thank you for the introduction. So my name is Brian Zhang, and I'm a graduating student from Indiana. Today, I'll be presenting our work, Demystifying Exploitable Bugs in Smart Contracts. This is a joint work with postdoctorate Zhang from Purdue University, Dr. Wen Xu from Georgia Tech, and Professor Zhiqiang from Ohio State. So, what are smart contracts? Well, smart contracts are automated programs running on the blockchain system, which is a public decentralized ledger. Since their conceptualization in 2008, smart contracts have reached a market capitalization of $1.19 trillion as of this May. There are numerous blockchains, such as Ethereum, Solana, and Polygon.
I'm testing the micro.
Servicing millions of daily transactions on countless blockchain-based products and services. So, however, similar to traditional software applications, smart contracts are made by developers and are hence susceptible to human errors. Exploitable bugs in smart contracts have caused a significant monetary loss. At the time of this research, $1.57 billion were exploited from various smart contracts, despite substantial advances in smart contract security. Therefore, we believe it is interesting to understand the effectiveness of existing techniques to detect real-world vulnerabilities, the categories and distributions of bugs that cannot be detected by existing tools, we call these machine unauditable bugs, and how we can further improve these existing techniques. However, it is first important to note some key differences between smart contract vulnerabilities and traditional software vulnerabilities. Traditional software security vulnerabilities usually have a set form. For example, buffer overflow or information leak. On the other hand, smart contract security vulnerabilities are generally more diverse, citing violations in domain and application-specific properties. Additionally, smart contracts are a direct linkage between software and money, and exploits usually indicate a direct monetary loss. So now we introduce our threat model. In our threat model, an adversary is a smart contract user who crafts special inputs in order to exploit the on-chain contract and to further cause monetary loss. Therefore, we consider attacks such as insider attacks, which are attacks launched by privileged users, spam attacks, and scam attacks as out of scope. Also, exploits originating from or having parts that are off the blockchain are also out of our scope. So now we introduce our research questions, which are: how effective are existing tools? What are the categories and distributions of machine unauditable bugs, where auditing is bug finding in smart contracts, and machine unauditable bugs are bugs that cannot be detected by existing tools? How difficult is it to audit exploitable bugs? What are the root causes of machine unauditable bugs? What are the symptoms and fixes of machine unauditable bugs? And finally, can they be properly abstracted such that automated oracles can be devised? In this presentation, we answered the first two research questions. The remaining 4 can be found in our poster in 315 in room 105. So, through guided auditing, or auditing with the help of our research, we earned $102,000, protecting $22.5 million in funds. We've also received recognition from notable smart contract security researchers, such as Patrick Collins and Bytes32. We also have a personal interview with Codarena, a security company hosting prestigious smart contract contests. And we also have a dedicated video from Fuzzing Labs, a research-oriented security company, explaining our paper. So now we'll introduce our data collection. We collected 462 bugs from 113 contests in Code Arena, a highly repeatable audit contest specializing in smart contract auditing. Typically, Code Arena contests last from 3 to 7 days, and developers place a bounty of $20,000 to $1 million in order to audit a smart contract before deployment. Participants from all around the world submit bug reports, which are then collected. And then, at the end of the contest, Code Arena judges will get together with the developers in order to provide feedback and to distribute the awards. So here are some more statistics about Code Arena. Most notably, at the time of this research, Code Arena had protected $2.8 billion in funds and had paid out $6.7 million in bounty. Out of those 462 bugs analyzed, we find that 341 of them are related to on-chain smart contracts and therefore are within the scope of our threat model. Additionally, we studied 54 real-world exploits, and we found that 44 of them fall within our threat model. And our study covers vulnerabilities discovered between the years 2021 and 2022. So this leads us to research question 1, which is how effective are the existing tools? To answer this, we studied 37 different tools, including Slither and Oyente, as well as testing oracles used by existing works to detect specific bugs, such as reentrancy bugs and precision loss bugs. We note that both of these techniques rely on general oracles or are hard-coded to be project-specific, such that they cannot detect functional bugs or violations of project business models. So, here's an example of a functional bug. In the first code snippet, we compare an amount with a variable debt in the ratio of 997 to 1,000, or 99.7%. However, in this bottom snippet of code, the ratio is instead 997 to 100, or 997%. This is incorrect behavior due to a wrong multiplier, and no existing tools are able to identify this kind of bug. So, how effective were existing tools? Well, we found that existing tools could find 70 out of our 341 Code Arena bugs and 9 out of our 44 real-world exploits, meaning that around 80% of all exploits cannot be detected by existing tools and are therefore machine unauditable. So this leads us to research question 2, which is of the machine unauditable bugs, what are their categories and distributions? We find that there are 7 such categories, and we list them as follows. The first category are price oracle manipulations, or manipulations of external price oracles in order to exploit a contract's funds. So, say you have a price oracle reporting on the price of 2 tokens, token A and token B, whose value is dependent on the ratio between them. As of now, token A and token B have the same value. However, let's say the supply of token A is decreased such that A is now worth 3 times of B. If this increase in price is used in an exploit, then that bug corresponds to a price oracle manipulation bug. Our second category are erroneous accounting bugs, or incorrect implementations of domain-specific financial models. The previous example with 2 code snippets was a demonstration of an erroneous accounting bug. The third category are ID uniqueness violations, which are a misuse or lack of access control in ID-specific functionalities, such as addresses or keys. Say, for example, let's say smart contract user A has a vault, which can be opened by a key that user A possesses. However, let's say we have a completely separate smart contract user B, who also possesses a key that can unintentionally unlock A's vault. This is an example of an ID uniqueness violation bug. The fourth category are inconsistent state updates, where internal contract storage is not completely updated after a state change. The fifth category are privilege escalation bugs, when unexpected business flow can lead to access control override. The sixth category are atomicity violations, where certain action sequences modify value and uses by other action sequences. And the seventh category are contract-specific bugs, which are bugs that have a very low likelihood of appearing in other smart contracts. So, in total, machine unauditable bugs can be classified into 7 categories, with around 85% that are not project-specific, and that bugs in most categories have general abstract models which may serve as oracles for future automated tools. More findings, including that different types of projects are prone to different types of bugs, can be found in our paper and also at our poster. So, as previously mentioned, we used our research and guided audit to earn $102,000, protecting $22.5 million in funds. We found 15 critical vulnerabilities with their distributions listed as follows. We particularly focused on price oracle manipulation bugs, as well as privilege escalation bugs, finding 2 and 4 of each category respectively. So, in summary, more than 80% of exploitable bugs are beyond existing tools, and this is largely due to a lack in describing and checking of the corresponding domain-specific properties, for example, general testing oracles. And the 80% of exploitable bugs that are beyond tools, called machine unauditable bugs, can be classified into 7 categories. One of the categories, corresponding to 16.2% of the total, is project or implementation specific, such that general oracles may not exist. However, the remaining 6 categories have clear symptoms and can be properly abstracted such that automated oracles may be devised. Our paper tries to raise the incentive of security researchers to develop automated oracles for machine unauditable bugs in smart contracts. So here are a couple of related works to our research. And thank you so much for your attention. Please stop by and see our poster in meeting room 105 at 3:15 p.m. Here's a QR code to our poster, and here's a QR code to our GitHub, which has surpassed 1,000 stars since this April. Thank you again, and yeah, that's it.
Any questions?
Thank you for a very interesting talk. So I was wondering about the definition of machine unauditable. Thank you. So it seems like you only look at static analysis of the smart contract itself to decide if it's machine unauditable, because for things like price oracle manipulation, you can look at the transactions that are actually happening and decide if the price oracle manipulation, and same thing for privilege escalation. So could you comment on that distinction?
Okay, so we consider machine unauditable as like unfindable by existing tools, which means machine auditable means that there are existing tools that can define that can find them. So when you talk about like price oracle manipulation bugs, you mentioned that because it's dependent on like the transactions what do you call machines that they can't sort of recreate, right?
Well, you know, there was a paper, I think, at Usenet Security last year where they detect price oracle manipulation by monitoring transactions, for example. Mm-hmm. Or same thing for some other kinds of bugs you have. So I'm curious as to where you draw the line between something being unauditable and something being, not visible at the code level.
Well, I guess that the way we decided that it was whether it was a machine auditable or machine unauditable was that we actually looked. So we based it first of all on 37 tools, which their categories are listed there. And what we did was we went into their research papers, and then we looked at what was the scope, what could they find. We also ran some, but we mostly used what was included within their research papers. So it's basically we used the scope. So like what I'm trying to say is that the scope of those tools that we looked at, I guess they just did not did not cover price oracle manipulations, or when we tested it, we could not find it. So I hope that answers your question.
Thank you.
More questions? I have one question. I think you already mentioned that from the 7 categories you can abstract the symptoms. I'm wondering that, do you have any suggestion to the future research? How can they improve their machine to detect those categories?
Well, I guess more specific oracles are needed, because right now general testing oracles are very broad. I mean, and they do a lot of work. So if we were to look at distributions, so this is why I particularly mentioned our vulnerability range is from the years 2021 to 2022, because if we were to look at previous years, we'd find that bugs that are currently like out of scope as of this study were not, and their distributions would be much larger. And because of those general testing oracles, we were able to completely get rid of those categories of bugs. So for example, like reentrancy and precision loss are not very common in our study. While perhaps 2 or 3 years ago, they would have been maybe the number 1, number 2 most popular bugs. So yeah, so then I just believe that for future studies, future studies will need more specific general testing oracles.
All right. Thank you so much. So please thank the audience.
Hello everyone, I'm Parvez Mahbub and today I'm going to present our work on explaining software bugs leveraging code structure in neural machine translation. I've done this work with the collaboration with Mohammad Masudur Rahman and Wahiduzzaman Shubho. So let's start by why should we care about explaining software bugs actually. In the past couple of decades, there has been numerous works on automatically finding the location of the bug or predicting different bugs in the software codes. However, these bug localization or defect prediction tools actually outputs certain parts of the actual source code without providing any explanation about why this tool thinks this particular line could be buggy or defective. Therefore, it is the task of the developers themselves to read through the code, understand them, and make reason about why this particular code segment is buggy. Reportedly, developers spend 50% of their time comprehending code during software maintenance. To reduce this hassle from the developers themselves, in this paper, we present BugsDistinguished, a novel transformer-based generative model that generates natural language explanation of software bugs, learning from thousands of bug fix commits. BugsDistinguished can leverage code structure in explanation generation by applying structure-based traversal on the source code. It is trained on both buggy and fixed version of the source code that enables it to reason about different buggy code patterns. Our evaluation on bugs pattern reveals that the explanation generated by BugsDistinguished are understandable and good according to Google's AutoML translation documentation. Furthermore, our developer study reveals that only 7% of the explanation generated by BugsDistinguished are inaccurate. So, let's talk about how actually BugsDistinguished does this explanation generation. This is the schematic diagram of BugsDistinguished training phase. As the input, BugsDistinguished takes thousands of bug fix commit, and from there, we pass them to our generate defect phase. I will be talking about defect in a later slide in detail. But what it essentially does is takes the structural information of the AST of the source code and embed that structural information into the source code themselves. Then, after this phase, we have two different variants of our source code. The first one is the defect sequence of the buggy code version, and the second one is the defect sequence for the bug fix version of the source code. And we pass them to the discriminative pre-training phase. During this pre-training, the model has access to both buggy version of the source code and bug fix version of the source code, and the model essentially learns to differentiate between the buggy code structure and fixed code structure. When the model is equipped with the knowledge of buggy code patterns and their structure, we perform the fine-tuning phase. During the fine-tuning phase, as it is supposed to do, it takes the buggy version of the source code as input and corresponding commit message, or as we call it, the explanation, as the output. And as the output of the fine-tuned model, we have our final version. Now, during the explanation generation phase, the model takes both a buggy source code and a sequence of lines as input to explain a particular segment of a source code document. From these line numbers and the source code itself, it generates the corresponding def-SBT sequence. And we pass the def-SBT sequence to the fine-tuned model, and finally it outputs the generic explanation. Now let's dive detail into the def-SBT sequence generation. For the illustration purpose, let's consider this particular commit diff, but if you think this particular commit diff is too much noisy to understand what's going on, let's convert them to buggy version of the source code, which is highlighted in red, and fixed version of the source code, which is highlighted in green. If you look carefully and differentiate between these two different variants of the same source code, their difference is in the buggy version of the source code, the sanitize function is called inside the for loop. On the contrary, in the fixed version, the sanitize function is called outside the for loop. Now, if a particular model treats the input sequence as a sequence of token, then the difference between this particular source code documents are just two single white space. Therefore, it is quite harder for models to learn and differentiate between this kind of buggy code patterns. But if we convert these particular code segments into corresponding def-SBT sequence, you can clearly see that their difference is much more noticeable now. In the buggy version of the source code, the for loop is ended by the end of the whole sequence. On the contrary, in the fixed version of the source code, the for loop ends at the middle of the sequence, and after the for loop, the expression to call the sanitize function is there. Therefore, when we have this kind of structural information embedded in the source code, it is much more easier for the models themselves to understand and differentiate different buggy code segments and their patterns. To evaluate the performance of BugsDistinguished, we perform both automatic metric evaluation and human evaluation. During our experiment, we have curated a new dataset comprised of data from 10,000 GitHub repositories, GitHub Python repositories, and from there, we extract 150,000 bug fix commits. Among them, we keep 110,000 commits for the training phase and remaining 40,000 for the validation and testing phase in the pre-training and fine-tuning phase. In our model architecture, we use the T5 architecture to structure our model, and there are 50 million parameters to tune from. We use Roberta tokenizer to tokenize the input sequence. Now, if we look about the metric evaluation, we have used 3 different metrics to evaluate BugsDistinguished. The first one is BLUE. Definitely, if you are familiar with any generative text, BLUE score is the most common metric to evaluate any generated text. It is basically calculates the n-gram overlap between the input reference text and the generated text. However, BLUE score is not aware of the semantic nature or the semantic meaning of the reference text or the generated text. That's why we incorporated another evaluation matrix, namely semantic similarity, that takes the semantic meaning of the text into input. Finally, we have exact match, which is essentially the same as string equality operator in any programming language. Now, when you look at the metrics themselves, it is quite evident that BugsDistinguished can outperform any other baselines we have used in our study. But we also have to take account in the subjective nature of our task. We are generating explanations, and the usability of the explanations depends quite on the developers themselves, how the developers themselves perceive this explanation. Therefore, we also perform a developer study with the help of 20 developers from 6 different countries who has programming experience of 1 to 10 years and bug fixing experience of 1 to 7 years. We provided them with 15 different buggy source code segments, their generated explanation with the baseline techniques. And we asked them to evaluate the accuracy, preciseness, conciseness, and usefulness of the generated explanations. And in this figure, we summarize their responses. Dark red means strong disagreement, and dark red means strong disagreement, and dark green means strong agreement. And you can clearly see that among all the options, BugsDistinguished has the least amount of disagreement and the highest amount of agreement. And this quite resembles the performance structure of the automatic evaluation metrics themselves as well. Now, so far, all we have talked about are numbers and different figures, but how does the explanation generated from BugsDistinguished actually looks like? To illustrate that, let's consider this particular example. In this bug fix commit, the buggy version of the source code tried to scrape some lyrics from a particular HTML page, but sometimes the code crashes. Now, the ground truth or the commit message of the bug fix commit tries to explain what is problem with the particular source code segment, and it says, fix a bug where the lyrics wiki feature would try to unscape an empty or none response from the crash. Now, if you look at the explanation generated from the baseline techniques, either they are not informative enough or not much related to the actual ground truth. But BugsDistinguished says, fix crash when lyrics not found, which expresses the same information as the ground truth, but in a much more precise nature. Now, in the past couple of months, actually, ChatGPT taken over the whole software engineering community, and we also asked ChatGPT, what is wrong with this particular code segment? And ChatGPT threw up a bunch of code segment and a bunch of text which is much noisy, so we again asked it to summarize this explanation, and it says the code is missing a line that assigns a variable to the lyrics variable. If you look at the ground truth again, that has nothing to do with the actual explanation. So without our novel structural information and the knowledge about different buggy code patterns, it is much more harder for any language model, large language model itself, to reason about different buggy code patterns. Finally, to summarize, software bugs not only claim precious development time, but also cost billions of dollars each year. Therefore, to reduce the hassle of the developer and the cost, we propose BugsPlaner, a novel technique that generates explanation for the buggy code. According to our human evaluation and automatic metric evaluation, BugsPlaner outperforms the baseline. And finally, we want to acknowledge that this work was supported by MITEX Accelerate International Program and our industry partner, Metabop Incorporation. Thank you, everyone, and I'll be open for questions.
Any questions?
Thank you. This is Shoigot from University of Saskatchewan. Nice presentation and nice work. So I find that you use semantic similarity as a measure. So semantic similarity, do you use any standard metric, or how did you measure this similarity?
Yeah, that is an interesting question. Thank you. And I wanted to explore more on that during my presentation, but definitely due to time limit, I couldn't do that anyway. In an ICPC paper in 2022, there was a study trying to explore an alternative for metrics like Blue score, and they had 4 or 5 alternatives that they come up and performed a particular human evaluation to understand what automatic metric evaluation can align the most with human judgment. In their study, they found that they generated a representation using sentence BERT. For each of the input text, they generated a representation using sentence BERT. Then they performed cosine similarity based on the representation of the sentence BERT vectors, and that aligned the most with human judgment. So in our study, we used the same evaluation. Thank you.
Thank you. Do we have one more quick question? I have one quick question.
Absolutely.
So I'm not sure if I missed anything, but how do you get the ground truth data for the explanation?
Actually, for the ground truth data, we have used the commit message from the bug fix commit. So we have the buggy version. When it is fixed, then generally the commit message explains what is changed, and we can consider them as the explanation to understand the bug. So that is our ground truth. Thank you.
Thank you so much. Please join me thank the presenter one more time.
Hi. Thanks for the introduction. Hello, everyone. Thank you for joining this talk. I'm Zheng, and it is my honor to present here. Today, I will be sharing our research on scalable conversational static tender analysis for sensitive data tracing on industrial microservices. This is a joint research with Jiang, Liao, Wu, Peng, Youshuai, Erci, and Zhong. In recent years, there has been an increasing demand for tracking sensitive data in the industry. With stricter cybersecurity measures, it is crucial to detect the data leak when confidential information is exposed to untrusted environment. For example, let's consider a case where secret information marked as private will be loaded by a query function in service 1. This private data is then used by another function or service for specific purpose. Finally, this low secret data will be handled and stored into another database. To trace the propagation of sensitive information in this scenario, tender analysis techniques are used. However, existing tools face challenges in efficiency and accurately analyzing microservices due to the scalability issues, low recall rate, and the imprecise result. Existing standard tender analyzers, such as FlowJoy, Ntent, F4F, and Zhou Infern, face scalability issues when applied to large-scale industrial microservices, such as the software-based application. This application consists of multiple modules with over 10,000 classes and include the runtime code, dependencies, framework, and the platform SDK. The sheet size of the industrial microservice application with jar package often exceeding 100 megabytes, along with a large number of service maps, pose significant challenges. In such large-scale microservices, the interested fields that need to be chased are usually thousands of thousands as well. The huge size of the obtained core graph poses challenges for executing precise, context-sensitive inter-procedure analysis using the traditional top-to-down stability analyzer. A concern, especially when performing the field-sensitive analysis, as it can result in lengthy analysis runtime and the excess memory consumption. Recall is another obstacle for steady tender analysis. Most existing analyzers suffer from low recall rate due to the incomplete code graph used for inter-procedure analysis in industrial microservices. Previous steady tender analyzer built a code graph based on the prebuilt code fragment before analyzing the data propagation. However, obtaining a complete code graph in large-scale industrial microservices is challenging due to the complex framework behaviors, such as the AOP, IOC, message service, and the event call. Manual modeling of this behavior is possible, but costly and time-consuming, and it usually requires significant human resources. Furthermore, ensuring all framework behaviors are property mode is difficult. Missing any framework behaviors result in the corresponding caller-collier relationship being absent from the program, reducing the recall rate of the tender analysis. Precision is another significant concern for steady tender analysis. Most existing tools tend to generate over-tainted analysis results due to the lack of precise tender checking in complex containers, which will generate a large amount of false positive results and make the result useless. To address this challenge, we have proposed a compositional field-based steady tender analyzer, which is fast, scalable, and provides comparable precision. Our compositional analysis approach performed the out-of-order analysis, and it will generating field-based information propagation summary for each map, and output a context-sensitive field-based information propagation graph. Generally, it contains two phases, the intra-procedure summary building and the inter-procedure summary building. Our compositional tender analysis approach will start analyzing from any function randomly. The field-based analysis is executed on each statement, generating the data propagation summary for each function. This summary describes the data propagation and maintains the context information. The generated function summary are reusable in our compositional analysis when the same function is involved with different parameters. This feature of compositional analysis enhances the scalability and enables the context-sensitive judging on sensitive data. To support the compositional analysis and increase the recall rate, we choose field-based analysis instead of field-sensitive analysis. The field-based analysis focuses on distinguished fields of the same kind rather than distinguish the instance of the same type. For example, let's consider two microservice classes, the handler and the task interceptor. The source data is logged from the request, and they are two things, the database insert map and the log print map. In this case, due to the interceptor configuration usually being set in the XML, the interceptor invoke function is injected and executed before bar is invoked. As a result, it includes two potential sensitive data leakage. One is from foo to the database in the bar. Another one is from the foo to the log file in the interceptor invoke function of the task interceptor. Most steady tender analyzer can easily detect the first leakage to the database, but you will usually fail to find the second leakage if the interception mechanism defined in the Spring XML file is not correctly modeled. In contrast, our field-based analysis treats all sensitive fields of the mode class as the same everywhere regardless of different instances. This allows us to identify the propagation of the sensitive field to both the database and the log file without modeling the interception mechanism in the Spring framework. Furthermore, we have implemented a pre-processing module that enhances the analysis precision in circle statement and the container operation. It includes code transformation and the modeling to handle AOP info. and the container operation code. Additionally, a database operation modeling module extracts all the SQL statements and establish the relationship between the variable and the database column. To evaluate the performance of our conversational field-based analyzer, we have implemented and run our tools on two benchmarks, which are the open source benchmark, micro benchmark that's provided by Entertainment on their FSE paper, and the intergroup production benchmark. The open source micro benchmark is contributed by the industry expert, include the cases developers are concerned with. The production benchmark includes more than 1,000 core production microservice application of intergroup. Here we randomly choose the result of 6 most frequently used microservices. The total line of the code is more than 5 million. To evaluate the performance of our approach, we use the open source micro benchmark. Our approach achieved a precision of 100% and a recall rate of 93% on the micro benchmark in the open source micro benchmark. And our tools failed to find any taint propagation paths in evaluation in 2 cases. After an in-depth analysis, we found that these 2 classes failed because of using a Java object class object as a source for the field-based analysis. To evaluate the precision, recall rate, and the time consumption for our tools, we test our approach on the production benchmark and compare it with N10 and the P10. In the production benchmark, our analysis outperformed existing tools like N10 and P10 with 30 to 45% increase of the recall rate and the 25 to 35% increase on precision on average. Furthermore, our tools demonstrate the efficient performance. Even on largest industries microservices, our tools only run in minutes level. In conclusion, our field-based conversational steady tender analysis provide a scalable and precise solution for tracing sensitive data in the industry's microservices by overcoming the challenge of scalability, incomplete code graph, and imprecise results. Our approach enables efficient and accurate analysis and make it available tools for enhanced data security in the industry. That's all for my talk. Thanks for your attention, and I'm happy to answer any question you may have.
Thank you so much. Do we have one quick question? Okay, so I have one question. It's very interesting that you also measure the computation time and show that it's very much more faster, but I'm not sure why it is faster, and can you explain more about that?
Yeah, because in our conversational analysis, as we mentioned before, the summary can be reused. It's reusable for the repeat function call. So if the invoke has been summarized, when this function be invoked in different function call with different parameter, we can just reuse the summary to compute the new propagation path rather than repeat the whole analysis. So it could make the analysis more faster.
Thank you so much. So please join me thank the presenter again for his presentation.
Hello everyone. Today I will talk about our study understanding and detecting on-the-fly configuration bugs. Software today are highly configurable. They usually have hundreds of options for users. The figure on the left shows the number of configuration options in some popular databases and web servers. Also, the number of options is continuously rising as the software evolves. Software systems usually load configuration files during startup phase. On the other hand, systems also support updating configuration at runtime to provide persistent service. For example, about 63% options in MySQL support runtime updating. and the number in NGX and squid is over 95%. However, on-the-fly updates make configuration design more completely, and it may lead to unexpected results like crashes or functional errors. We refer to the bug caused by on-the-fly configuration updates as OC bugs. Let's see an example of a real-world OC bug. The option is used to record slow query logs. The user changed the option value from false to true, but the system did not record related logs. This is a form of functional error. Some work reuse official tests and oracles to detect configuration bugs. For example, specs inject configuration errors into the system and evaluate system behavior regarding misconfigurations. However, these official test cases are not specially designed for on-the-fly configuration updates, so it's hard for those works to detect OC bugs. Many other works generate new test cases to expose bugs. Fuzzing requires easy-to-observe symptoms as test oracles, such as crashes or memory sanitizers. However, OC bugs may not always lead to aware symptoms. Therefore, the challenge of detecting OC bugs is the lack of effective test oracles. In this paper, we conducted the first study on OC bugs based on 70 fail bugs from fail popular systems. We studied the three questions: the symptoms, root causes, and the trigger conditions of OC bugs. OC bugs could cause the system to crash, hang, memory leak, and functional errors. We found most of OC bugs result in functional errors that have no easy-to-observe symptoms. Therefore, most OC bugs are hard to detect by the existing technology like fuzzing. During the study, we found users frequently compare the effect of an option as loaded at startup or updated on the fly, and report bugs if not consistent. For example, in the MyCircle bug, the user found the effects of the same option value are different, then identify the bug. Therefore, we propose the key set of detecting OC bugs. The value of one configuration, either loaded at startup or updated on the fly, should have the same effect on the program. In order to identify OC bugs more effectively, we also studied root causes. It can be classified in two types. The first one is incorrect propagation of configuration-related variables and account for nearly half of the bugs. We refer to it as propagation bugs. And the other half is incorrect usage of the variables. We call it usage bugs. This classification is straightforward because every variable should be first propagated and then used. Propagation bugs happen during propagating configuration variables. The detailed classification can be found in our paper. In propagation bugs, the value of some configuration variables are incorrect. Therefore, we propose Oracle 1 of internal effect to detect propagation bugs. The value of configuration variable should be the same no matter the options are loaded since startup or updated on the fly. Usage bugs are about using those configuration variables. In those bugs, the value of configuration variables are correct, as they can only be detected by examining external behaviors of program. Therefore, we proposed Oracle 2 of external effect to detect usage bugs. The output of the system under test should be the same, no matter the options are loaded since startup or updated on the fly. The findings inspires us to use metamorphic testing to detect OC bugs. We designed Parachute. It contains two main steps. First, it generates metamorphic test cases for the target options. Thus, we get a pair of test cases in this step: the test with configuration updates and without updates. Second, it conducts the test and identify OC bugs based on the two oracles: internal effect and external effect. Parachutes leverage and mutate the exciting test suites to generate on-the-fly tests. The main challenge of this task is a huge testing space. For each test case, parachutes need to generate a large number of mutations, since one option may have different updating values, times, and dependencies. To address this challenge, we conduct a study on the trigger conditions of OC bugs and get 3 conclusions to guide test generation. First, we found both valid and invalid options values to be taken into consideration. Therefore, we use spec to infer configuration constraints and simple valid values. And we use CEIT inspector to sample invalid values. Second, we found most OC bugs can be triggered by updating one option once. It means performing one update operation is enough for the majority of OC bugs. Finally, we found in most OC bugs, the target options do not depend on other options, or the dependency can be obtained by program analysis. Therefore, we use specs to obtain configuration dependencies and satisfy the control and the value dependency for the target option before testing. After that, Parachute generates 2 executions for a target option. The first one starts up with config A as V0 and do not update the option. The second one starts up with config A as V1 and update the option into V0. We record the output of each test after the update is conducted and compare the output to detect OC bugs. The internal effects are value changes of configuration variables. Therefore, Parachute first conduct hand analysis to find configuration variables, then instrument the source program to record them. The external effects are program behaviors that can be observed outside the program. Parachute record outputs, clocks, and counts during the test. There is also a challenge. The effect of option updating may not happen immediately. Configurable systems generally allow delay usage of the updated value after they complete the current executing transaction. For example, the output of the select operation is affected by the old value of the option. Although the two outputs are different, it's not a bug, but false positive. Parachute needs to avoid false positives caused by the delay usage of options. Therefore, we propose 3-stage testing approach to identify false positives. The more detail could be found in our paper. We evaluate Parachute from 2 aspects: the effectiveness on detecting exciting OC bugs and new bugs. We first reproduce 38 studied OC bugs. To avoid overfitting, we repeat the bug collection method on MyRealDB and HTTPD and reproduce the 18 bugs that were not included in the study. We also compare the result with Staccato. Staccato is state-of-the-art tool for detecting configuration update bugs. Parachute successfully detects 75% of the exciting bugs, while Staccato can only identify 27% of them. This is because Staccato only checks whether configuration variables are changed after configuration update. We also apply Parachute on the latest version of the 7 systems to find new bugs. We successfully found 13 new bugs in 5 systems, and 11 of them have already been confirmed or fixed by the developers. In conclusion, we conducted the first study on OC bugs from 5 systems to understand the features and root causes. We designed Parachute, an automatic framework to detect OC bugs. We evaluate Parachute on 7 systems. Parachute can detect 75% of the known OC bugs and 13 unknown bugs. Thank you for attention. I'm happy to take any questions.
Thank you so much. Do we have questions from the audience? Yep, what questions?
Hi, thank you for the great presentation. So I do have one question about, you mentioned that the tool you have can only consider one configuration parameter during the changes. So have you ever seen any OC bugs that are related to configuration dependencies that involving multiple option changes?
We find in most of OC bugs, the target option do not depend on any other options, or the dependency could be obtained by program analysis. Therefore, we could satisfy the control and value dependencies before the testing.
Okay, thank you.
We can have one more question. Yes.
I have a question. So when you generate a test, if the test is a flaky test, so how do you handle it?
Thank you for the question. Yes, the flaky test do affect the effect of parachute. It makes some false positives that parachute for parachute. We now just pre-do the test before conducting parachute to select some flaky test, but it's really a challenge for us. Thank you.
Okay, thank you.
Do we have more questions? Okay, so thank you so much for your presentation. Please let me thank the presenters again.
So this is a registered report. We registered this work last year at MSR and now conducted the study. And the goal is basically to look beyond what we usually do, accuracy, recall, and whatever, and try to find out how these measurements relate to actual costs if you put your models in operation. And we do this in the context of defect prediction. So you don't need to know defect prediction to get the general idea. You take a piece of software, measure something about it, put it into a machine learning model. You get some output. This piece of software is defective. This isn't. Then somebody does something on it, right? So this is, the outputs in an accuracy measurement is where you usually stop. But in reality, somebody would do something, right? So they would take a prediction and say, I do additional tests here, something like that. And maybe find a bug or miss a bug, or you predict something as not defective where you miss a bug. So this is reality. And the question is, how do we measure this? Well, we do this with machine learning metrics. So precision, recall, F-measure, MCC. There's some cost-related stuff like how many bugs do I find when I look at 20% of the code and stuff like that. But yeah, the question is this really related to profits? So a couple of years ago at ICSE, I already presented the results of a TSE paper we had where we basically did a cost model. And there we found there's actually several cost factors. And so you need to introduce a defect prediction model. Those are costs, those amortize over time. It really depends on the tool market. So we don't really know about those. But we know that there will be additional costs for quality assurance or saved costs for quality assurance based on what you're doing. You have costs for correction of defects. And ideally, you want to save costs, right? So we don't only want to spend money, we also, in the end, want to save money by basically having a cheaper development with the same quality or, for the same price, less bugs. So in both cases, we save something. And because we rather wanted to look at all at cost, we just say we don't save money by finding bugs faster, but rather we have costs when we miss bugs. But that doesn't really matter. But in the end, this allows us to model costs as a formula where we add up these terms. We were able to prove some nice boundary conditions on these are the costs of defects. I really can't go into the theory here because I have about 5 minutes to talk about a journal paper, which is already challenging enough. And our research question in the end is really, how is this correlated? These model performance metrics on the one hand and
the actual costs on the other hand. And we did a fairly sophisticated study, so I won't walk you through all of this because 5 minutes. So we took a lot of releases from projects, we trained random forests based on best practices from research, we collected our variables for this, basically we measured all these metrics, plus a lot of confounders like project size or how many defects are there in these projects. Then we trained a model to get these relationships. We did it linearly, we did it with a decision tree, we did it linear with a random forest. We looked at the confusion matrices to then get a theory. This is how they are related. And then we repeated all of that with independent data. So that before was a bootstrap experiment, and then we said, okay, if this is a real relationship, we should find it also when we do cross-project defect prediction or within project defect prediction. If you know the terms, good. If not, doesn't really matter, it's just different experimental data. So we generalize this and see if our theory holds. So that's the idea. And we then get lots of data, so we have nice distribution of costs. We actually find that, so I want to point here really quick. In a lot of cases, the defect prediction models are not able to save costs at all. So it's actually a coin flip whether you can save costs. So that's actually a key result we have, so be aware of that. Defect prediction doesn't work most of the time. But in the end, we found that it's actually roughly a log normal distribution of cost saving potential with a mean of around 1,000 lines of code. And then we looked at these correlations with other metrics. And well, I don't expect you to read this, but the idea is, this is the experiment where we built a theory on, and we basically found here clusters of nice related stuff or inversely related stuff. So we found groups of metrics that somehow belong together and have the same relationship to costs. And well, here the metrics are all the same and the groups are basically vanishing. So in other words, the relationships between metrics themselves and between metrics and costs are completely different on different data sets and different experiments. In other words, you cannot look at correlations between these and expect that they hold in other data. So what worked then in our bootstrap experiment, and we were able to predict then how the costs would be based on standard machine learning metrics, does not work anymore when we want to generalize this to a new experiment. So what does this mean? Well, our metrics are not related to costs in general. And well, we somehow expected that this might be the case because we actually have a theory why this is not the case, because, well, we have a cost model. And one key factor of the cost model is that when you do quality assurance or testing or whatever, it costs more to test something larger, right? So lines of code might not be the perfect estimator for this, but maybe there's a better one, I don't know one. So lines of code are not evenly distributed. But these metrics usually assume a true positives cost something and a false positives cost something and so on, and doesn't take this individual cost into account. Some models do, but then not all factors. And that's the big issue. We cannot just use the confusion metrics, basically also beyond defect prediction, to evaluate something where the costs are really unevenly distributed per instance. So this is a general result, actually, that goes way beyond our paper. And, well, to conclude, those who were at my talks this morning already saw one warning label. Now I have another one. The metrics you're using to measure the performance of your model is not necessarily related to the cost effectiveness, even though we usually assume that. So conclusions drawn then might be unreliable. So for you as researchers, 2 messages. If you want to know about costs of something, measure costs and not some proxy. Try to model the costs. And if you want to measure something else unrelated to cost, use that. So if you want to know if, I don't know, some feature is related to bugs, this doesn't matter for you. But if you want to know if your model is better when you put it in operation, this is for you. And well, the other one is, it works in about 50% to save costs. So maybe think about putting it in operation. Okay, the details are in the paper. I think I'm roughly in time, and then I thank you for your attention.
Thank you so much. Do you have one quick question? Yeah.
Hi, Stephen. I'm very happy for your excellent presentation.
so I enjoyed it. So if you provide with me some time, I have one paper discussed about, I proposed some measures to estimate the predictions in terms of cost, the remaining service time, and failures we may get from the prediction model. And as you said, it is correct, and we have to look into more into reality, so how much cost can be saved, and in addition to that, we have to look into like how does it really lead to the failures in a software if the prediction model is implemented in real world scenarios.
So if I understood correctly, the question is the following: the defect prediction model can then really prevent failures or something like that. Well, there are some examples of where these models were put into operations that are reported, but most of the time the companies are a bit reluctant to report too much on that. And the most famous example in that direction is just the failed experiment by Google a couple of years ago. It was reported at ICSE 2013. And there, the developers basically just didn't want to use it anymore because they acted on the model and the predictions didn't change. So there are really these socio-technical factors actually that we also tend to ignore and that I also still ignored here, which also play a vital role. So quite honestly, if anybody were to come to me right now and wouldn't have a strong incentive to put this defect prediction model into operation, I wouldn't recommend it to any practitioner right now. That's my honest assessment of this right now, and it doesn't seem good enough, at least based on software metrics.
Thank you so much.
Good morning, everyone. Thank you for the attention. And yes, as presented, my name is Sergio Moreschini. I'm from Tampere University, and I'm here to present you, as said, this work entitled "A Machine and Deep Learning Analysis Among SonarQube Rules, Product and Process Metrics for Fault Prediction." So what does it mean? So usually we have a situation in which developers spend most of their time just fixing, searching for bugs, refactoring code. So what we actually need is something that helps focusing on developing part and then also help you finding what are these bugs, how to fix them, and so on. So for this reason, multiple methods so far have been researched and analyzed to basically analyze the fault proneness of a specific part of code with the use of code smells, code metrics. So what we actually want in this work is to see which of these methods work best, which metrics are ideal, so that we can actually predict how it's actually going the development of the code. So the main goal of this paper has been to advance the state-of-the-art in fault detecting commit prediction by performing a deep investigation among several rules, project commits, by making use of machine learning and deep learning classifier. And to do so, what we actually did was dividing the work into these 4 different parts. So that in the first part, we actually wanted to analyze what is the fault proneness of the SonarQube rules. So we specifically use SonarQube as this static analysis tool. Then what is the fault proneness of the different process and product metrics that we can achieve still from the analysis of these commits. Then to what extent can this rule impact the performance of the prediction models that leverage processes and product metrics? And in the end, which one is actually our final goal by using this feature, and which is the best model that can actually help us to perform this fault prediction? So what this actually means in the end. So first of all, we performed the analysis of the SonarQube rules in the first part. So what we had was basically having the SonarQube rules together with the labeled dataset, and we performed different machine learning and deep learning analysis. Then we performed the logo validation, so that basically out of 29 different projects, we left one out at each time. We performed the training on the other 28, and then we performed the validation on the other one for all the different combinations. And then in the end, we got the result for the specific SonarQube rules. For the second research question, instead of analyzing the SonarQube rules, we analyzed what were the metrics, the products, and the process, specifically the one from Kamei and Raman. So basically the experience and how the project evolve with time, so what are the changing. Then as at the evolution of these results, so from what we got from RQ1 and from what we got from RQ2, we try to combine them. So seeing what is the, let's say, support that the SonarCube rules can give to all these other SonarCube metrics, product, and processes, so that how can this advance these other metrics that we found in RQ2. Then in the end, we evaluated what are the best combination of these metrics using this statistical test that is called NMA. And more information about this, you can find them on the paper. So, as you know, when you are working with machine learning and deep learning, a big chunk of what you get is the data. So it has a very high importance. So this work has been an extension on another work that we had at the beginning, in which we had this candidate project, then we did the analysis on SonarCube, and we extracted the rules, the types, and the metrics. For what was concerning instead the product and the processes, we used this process described from this work from Pascarella et al. So you can actually extract all of this information. And this data is actually available, and it's called Technical Depth Database, and has been used also in other work so far. But what was important in this specific work was that we perform a very heavy feature extraction, so that out of this 33 projects, we extracted the 29 that mean the most, because they had a very higher influence. And another important part is that we performed the oversampling using this smooth approach, so that as we had really unbalanced data, we tried to make the data more balanced so that both machine learning and deep learning approach were working better. So the final result is that deep learning models work best using a mix of all the metrics available, so by basically summarizing the results from the first 3 research questions. And another part is that the deep learning improved also thanks to, deeply improved thanks to the historical data considered, because as you can see from the result that I'm showing basically in this plot, you can see that when we are talking about the deep learning approach, so fully convolutional network or ResNet, this box plot show a very, very small difference between the first and third quartile. So these results are way more reliable than all the other ones that are just based on machine learning, so there is no historical information about them. And yeah, basically to conclude is that when we use product and processes metrics like Raman and Kamei, this can give us very good information about fault predictors. Then if we include the SonarCube metrics, we get an impressive accuracy performance, so that if we use deep learning and machine learning approaches, we can reach something like 95% of accuracy. Thank you for your attention. And that's all.
Thank you so much. I think we have one question.
Thank you very much. Great work. We did something more or less exactly the same, but not with SonarCube, but with PMD a couple of years ago. And I mean, SonarCube is very different, right? SonarCube looks a lot deeper and is not as superficial, so to say. So PMD is more like style. SonarCube also does lots of functional stuff. Mm-hmm. We found then that the difference was there significantly, but the effect size was relatively small of including the warnings. So here it looks like the difference is also there. It also looked higher, but I mean, it seemed like the performance was always pretty large with the deep learning models. So I'm wondering, have you measured the effect size? So I would be really interested in that.
Sorry, can you repeat the last part? I lost the last part.
So basically, how big is the difference, either in terms of accuracy or in terms of effect size, Cohen's D or whatever, between using, let's say, only static metrics or using only static and process metrics, and using that in combination with SonarCube rules?
Yeah, so as I was saying, trying to show in this point, can I get? Yep. As I was saying to you, like, the first part that I was trying to show is that this is basically resource question 1. So in here, we were only analyzing SonarCube rules. And even if you use a deep learning method, there is so much difference between the first and third quartile. So these results basically are not reliable at all. What we want to show by answering research question 2 and especially research question 3 is that SonarCube rules are not good enough by them. We need to use the combination between the rules and Kamei or the matrix rules in order to have at least this reliability, like they really need to be reliable. But if you use all of them, so the rules, the metrics, and Kamei, and even Kamei Ramal, you can have results that can be very reliable. So even if you use just machine learning, so that you don't have historical information, but just what is happening now, the information can be quite okay, but it's not reliable. So that was the main finding that we wanted to show. Okay. Did I answer your question? Yeah. Thank you.
Thank you so much. So we run out of time already. Thank you. And that's all for this session. Thank you so much for your patience.